This is the example, linear program example for feeding your pet. Okay, so this is the doctor recommends your pet receive at least 60 units of vitamin P and 54 units of vitamin Q each day. More is okay. However, your pet should limit the intake of substance R, which is in most pet food. And the pet store sells food number 1 and food number 2. You will buy both and mix together to get a special blend for your pet. The food number 1 contains 5 units of P, 3 units of Q, and 2 units of R for every gram of food. Food number 2 contains 4 units of P, 6 units of vitamin Q, and 3 units of substance R for every gram of food. Find how many grams of food number 1 and how many grams of food number 2 your pet should eat daily to satisfy the vitamin P and Q requirements while limiting intake of the substance R. Okay, we still use a table to help you to summarize this problem. So we have 2 foods, right? Food number 1 and food number 2. The first row is the vitamin P. In food number 1 contains 5 units of vitamin P. Food number 2 contains 4 units of vitamin P. And it says you must at least 60 units of vitamin P. So should be greater than equal to 60 total. The second row is vitamin Q. Food number 1 contains 3 units of vitamin Q, and food number 2 contains 6 units of vitamin Q. It says at least 54 units of vitamin Q. So at least means greater than equal to 54. Substance R. Food number 1 contains 2 units and food number 2 contains 3 units. Okay, so we want to limit intake of R. So that means we want to minimize what? Minimize intake of this substance R. Okay. So if we let X is the gram, we have X grams of, to mix a special blended food for pet, you need X grams of what? Food number 1. Food number 1. We need Y grams each day of food number 2. Okay, and we want to minimize. We use MIN to denote the minimize. Z is the units for the substance R for each day. We want to minimize Z. So for food number 1 contains 2 units of R, so its total have per gram. So this is the X gram, so it's 2X. And plus food number 2 contains 3 units per gram for substance R, so it's 3Y. So you plus together will be the total substance R the pet will intake. So this is we want to minimize this substance R, so which is Z. We use Z to denote the substance R. What is the constraint? The constraint is from these two. So the vitamin P, food number 1 is 5x vitamins. Food number 2 is 4y vitamins, vitamin P. So at least, so greater than equal to 60, right? And for the vitamin Q, 3 units for food number 1, 6 units for food number 2. So 3x plus 6y, this is the total vitamin Q. At least 54, so greater than equal to 54. Of course, because this is a real life problem, so x should be greater than equal to 0, y should also be greater than equal to 0, which is the first part, right, of this x coordinate, xy plane. So we set up, so this is the setup for the linear programming problem. So the first thing is you should set up this linear programming problem correctly. Otherwise, you cannot get the answer, right? So the next thing is you need to draw the feasible region, which is from the constraints. So xy should lie in this region, which is a system of linear inequalities, right? The system of linear inequality will give you a region which is called the feasible region. So now let's draw the feasible region for this problem. This is 10, this is 20, 10, 20. Okay, so the first inequality, which is 5x plus 4y greater than equal to 60. So we consider, we use different color. 5x plus 4y equals 60. Well, let's look at the boundary first, right? We need 2 points, right? If x equals 0, y equals 15. If y equals 0, x equals 12, right? So this is 15. This is 1, 2, 3, 4. So this is 12. So 12, 15 is here. Right, this is the 15, so this is the 0, 15. Yeah, just write 15. Okay, this is 1 point. The other point is 12. So this is 15. 1, 2, 3, 4. Okay, so this is 12. This is another point. Let's connect these 2 points. Okay, so this is the line. So which part? Let's plug in. And this origin, 0, 0. So 5 times 0 plus 4 times 0 equals 0, which is less than 60, not greater than equal to 60, not greater than equal to 60. So that means it should not, the region containing this point, so it should be above this line. Now let's look at another one. We use different color. Another inequality, which is 3x plus 6y greater than equal to 54. So 3x, let's look at boundary, plus 6y equals 54. Okay, so we have, if x equals 0, y equals 9, right? This is the x-intercept, y-intercept. If y equals 0, x equals 17. So this is 9. 0, 9. Which is here. And we have 17, so this is 15, 16, 17, for example. 17 is here. So 0, which is this point. We just sketch the graph, okay? It's not very accurate. Then we connect. Sorry. I didn't draw very well. Okay, so this is the line. 3x plus 6y equals 54. Then we need to find the sum. So, okay, so we also have x greater than 0, greater than equal to 0, and y greater than equal to 0, so it should be in this region, right? This is x greater than equal to 0, and y greater than equal to 0, so this is the region. So what is the final region? The final region, which is this part. Oh, sorry, I forgot which part should be the blue one. So it should, if you plug in 0, 0, 3 times 0 plus 6 times 0, which is equal to 0, which is greater than equal to 54? No. So it should not contain this point, so it should be here. Okay, so the final region would be in the first quadrant. This is called the first quadrant, right? Where x, y are positive number, non-negative number, so it should be here. So at last, the common region would be, this is the boundary of this region. This is the unbounded region, right? You can see on the other side we have no boundary. So the minimum value must happen at the corner, right? Since the problem asks you the minimum value, that means the minimum value must exist, right? So we don't need to worry about the exist or not. Okay, so this is the so we have some corner points, right? This is the corner, one corner, which is what? 15, 0, 15. This is another corner. This is the 17, 0. Sorry, it's not 17, 18. I made a mistake. $18, 0. Okay, so this point is 18, 0. Right here, 18, 0. So what is this point? This point is the intersection of the red line and the blue line, which is the solution for the linear system. The red line is 5x plus 4y equals 60. The blue line is 3x plus 6y equals 54. If you multiply 3 on the first one, it will give you that 15x plus 12y equals 180. If you multiply negative 5 on the second equation, it will give negative 15x plus minus negative 18, 5, so it's negative 30y equals negative 270. So if you add these two, okay, we use the elimination, right? So we add these two, it will give you negative 18y equals negative 90. So y is equal to 5. So if y equal to 5, you plug into here the first equation. 5 times x plus 4 times 5 equals 60. So this will 5x equals 40. So x equals 8. So this point is, the solution is, this point is 8 and 5. Okay, so you have 3 corners. So we list the table. One point 0, 15, 8, 5. Another one is 18, 0. This is the z values. Z is equal to what? 2x plus 3y. Okay, I write here. Just in case we forget. 2x plus 3y. So z here would be 2 times 0 plus 3 times 15, which is 45. This point gives you that 2 times 8 plus 3 times 5, which is 16 plus 15, which is 31. And the z here is 2 times 18 plus 3 times 0, which is 36. So this will give you the minimum intake of the substance R. Okay, so that means we have 8 grams of food number 1 and 5 grams of food number 2, which will minimize the intake of substance R, which is 31 units. Okay. So this is another problem. Right. So you see, we have the same strategy. The first one, if you're not very familiar with, because the words and the background is too complicated for the problem, right? So you'd better to use a table to summarize this problem. We use table, which is present here, right? Then we want to know from the questions, we want to limit intake of R. So that means we want to minimize the intake of R. So we want to minimize, write down the objective, which is to minimize the intake of substance R. So then we introduce 2 decision variable, which is x grams of food number 1 and y grams of food number 2 each day. Okay, so then we write down the linear programming problem, set up the linear programming. We want to minimize we use Z to denote the quantity of the units of the substance R. So Z is equal to 2 times X plus 3 times Y. Okay, and this 2 and 3 are from this table. Food number 1 contains 2 units, and food number 2 contains 3 units of R. Then we write down the constraint. Okay, this is the first constraint. It's at least 60 units for vitamin P, and the second inequality is at least 54 units for vitamin Q, and XY should be non-negative, right? So it's at least 0. So greater than or equal to 0, and Y is also greater than or equal to 0. So the next thing is you need to use the technique we learned in the system of linear inequality to sketch the region, feasible region, okay? So that means XY should be lies in this shaded region, the purple region. Then you use the technique we learned last previous section, so we can sketch the region, okay? And then we need to locate the corner point. Right? So here have 3 corners. Then we plug in this table, write down the corner points on the first column, and the second column is the z values. Then you plug in the corner point into the z function, the quantity of the substance R, right? How many units for the substance R for each point. So then you choose the smallest one would be your answer. So that means here is 8 grams of food number 1 and 5 grams of food number 2 each day will minimize the intake of substance R, which is 31 units. Okay, so these are the topics for the linear programming of which is a geometric approach to solve the linear programming problem.